Hi, my name is Olivia, and welcome back to Quantum Paper Review. Today we will be reviewing an exciting new paper published in Nature called Encoding a Magic State Beyond Break-Even Fidelity. And if that's a little bit of an intimidating title, please don't worry, because I have three of the authors of this paper here today, and I'm going to be interviewing them and asking them exactly what a magic state is and what it means for both us and the field that we have finally crossed this break-even fidelity threshold. We'll get started here in just a moment, and we'll be welcoming Dr.Takita, Andrew Cross, and Ben Brown from IBM. Hi, Ben. Thanks for coming down. Could you briefly introduce yourself and tell us a little bit about what you worked on in this paper?
I am a research scientist at IBM, mainly working on quantum error correction, and I supervise this project together with Micah.
So I'm an experimental research scientist, and I've been working mainly on quantum error correction related demonstrations. But more recently, I've been working on a large-scale demonstration using new capabilities, leveraging the dynamic circuits capability. So for this work, I was supervising the team.
My name is Andrew Cross. I've been a member of the research staff at IBM for a little over 10 years. I also manage the Theory of Quantum Computing and Information group. And right now, my focus is on research in quantum error correction. So for this paper, I contributed to some of the protocol development and also had some ideas for alternatives for magic state distillation.
So let's get right into it. What is a magic state?
Magic state is a special resource that we need to make a quantum computer do all the things it's supposed to do. So a quantum computer has to be able to do a certain set of operations to make an algorithm, and some of those are easy and some of those are difficult. Mm-hmm. And a magic state is a special resource that lets us do those difficult operations.
What are dynamic circuits exactly?
So dynamic circuits are new capabilities that uses classical communication in real time. So in a regular, say, static circuit, you would have some quantum operations in sequence that acts on qubits, and then typically there's a measurement at the end, just terminating the circuit. Mm-hmm. But in dynamic circuits, you could have measurements in mid-circuit, and then in the process, you could use the outcome of the mid-circuit measurements to act on the qubits. So you could have a measurement, the outcome goes to the classical processor, and then it tells the circuit to run another quantum operation. So it could be another gate acting on the same qubit or a different qubit. So this has to happen within the fraction of the coherence time of the device, right? Because otherwise, by the time the new feed-forward operation happens, all the results have been kind of messed up. Right. So it's important for these operations to have quickly so that you could reuse these qubits afterwards as well.
So in your opinion, Andrew, how does this paper fit into the wider context and the discussion about fault tolerance and error correction?
Yeah, so we often focus a lot on the first part of that, error correction. And that's because we know that this is an important and difficult challenge. And it's also something that a quantum computer, a fault-tolerant quantum computer, is going to spend a lot of time doing. Mm-hmm. But it's only half the challenge to realizing a fault-tolerant quantum computer. What we also need is we need to be able to transform and change that information that we've encoded. We have to compute. And so to do that, we have to build up what's called a universal set of operations. These are operations that we can compose together and approximate any computation that we want to do. So there are many ways to implement a universal gate set. And what we're looking for is a way that can tolerate a lot of noise. And so one of the leading approaches is called magic state distillation. It was discovered by Brapi and Kitaev. Mm-hmm. And so the paper that we're discussing today shows how, and in fact we demonstrate a small gadget that prepares high quality initial magic states.
Cool. And can you explain why some quantum states are what we call error prone?
We have to build a quantum computer out of real physical qubits in the lab, and these are getting better and better, but they're never going to be perfect, and we have to deal with these problems. So what we do is we take the information we want to put into a quantum computer and we encode it in what we call a quantum error correcting code, and this is where lots of these physical qubits that we build in the lab they all work together to protect some logical information from errors. Okay, and so then once we have this information protected, that's good, but then this also limits the operations that we can run, and this is what I mean by easy and hard operations that I talked about a moment ago. So there are some quantum states that are easy to make and easy to prepare and easy to manipulate, and some of them are difficult to make. And an example of those are magic states.
Got it. So why are the dynamic circuits, or why were they needed in order to make the magic state distillation happen?
So for this project, the state that we prepared, the CZ state, that's how we call the state in the paper. So to prepare that state in this error suppressed manner, you first encode the qubit in plus state. And you do that by first preparing the data qubit into plus states, O plus states, superposition states, and then measure the Z stabilizers. But to then prepare the CZ state, you need to be in the +1 eigenspace of this Z stabilizer. So, from the beginning, when you prepare this plus state by preparing this data qubit in plus state and then measuring SZ, the outcome is random. So it could be +1 or -1. So then if you measure a 1 from the stabilizer, then you need to apply this feed forward operation so that all the outcomes are in the +1 eigenspace.
So in your opinion, what is the most important one or two figures in this paper?
Yeah, so all the figures carry an important message. It's hard to pick a small number, but I'll just focus on the first two figures of the paper. So those figures outline the protocol that we implemented. They illustrate the high-level view of the protocol, as well as how it was implemented on our hardware. And so, I guess what surprised me about that is that it's somewhat of an unconventional approach to preparing magic states. We prepare a 2-qubit magic state. Turns out that the circuits can be adapted very well to our hardware. And I think this is what enabled us to see these performing so well and allowed us to get the result. And so seeing that kind of creativity from the team has left me feeling very optimistic about the possibility of finding even more improvements at other stages of this magic state protocol.
Cool. And in terms of IBM's plans specifically and IBM's roadmap for error correction, where does it fit into that?
Yeah, so let me start with some context. So correcting errors has a cost. So right now we actively use error mitigation to run deeper circuits and deal with noise. And the cost there is that we have to run the circuit many times. Now, eventually, we believe that if we want to run very deep circuits, we need to use quantum error correction. And that also has a cost. We have to take the information we want to protect and encode it into many physical qubits. And so the challenge is to find ways to do that in the cheapest way possible. Recently, IBM announced a new roadmap, an extension of the current roadmap out to about the end of the decade. And this new roadmap addresses this challenge of cost in many ways. So it has 2 tracks. The top track of the roadmap, the main track, is focused on quality, so improving the devices so that we can run deeper circuits. And error mitigation and error correction serve that goal of running those deeper circuits. Then there's a second parallel track, which is called our innovation roadmap, which is focused on the goal of building the technology and the techniques that we need for efficient error correction. So this includes things like pursuing more connected devices, and that's important because it could enable us to use more efficient codes. It also includes things like realizing and developing new theoretical ideas for gates, for fast decoders. So, and specifically the magic state experiment fits into this picture because what we've demonstrated is a small gadget that can be incorporated into a larger scalable protocol that ultimately reduces the cost of this universal set of gates.
And I know that one of the biggest sort of takeaways from this paper was that you were able to cross that breaking even threshold. Can you explain a little bit what the significance of breaking even means?
Yeah, that's right. Well, so break even shows break even is maybe a milestone showing that error correction is really working. So we have these physical qubits that are a little bit noisy, and as I said, we want to use these physical qubits and make them work together as an error correcting code that's maybe supposed to do some kind of a task. Mm-hmm. And if these qubits are good enough, then they can work together in such a way that if some of them are going wrong, we can work it out and fix it, and they should all work better than the sums of their parts. So what break-even means is that we've really shown that the task the error-correcting code is performing is working better than what we could have done with the physical qubits, and that's what we show in our paper.
And that is a huge milestone.
Yeah. That's a good demonstration.
Okay, cool. So I think you kind of already answered this just now, but what makes the overall findings of this paper so exciting to you?
Yeah, well, it really shows that the physical qubits that we're making, the hardware we're making, is getting good enough that we can really show that error correction is working now. Like, error correction only works if the qubits are below a certain threshold in terms of how much noise they experience. And that's a really hard thing to reach. So a break-even result shows that the superconducting qubits that we're making are really heading towards some era where we're going to be able to run error correction.
Right. So I guess just to rephrase that, it means the qubits themselves are physically good enough at this point that we can start implementing the theoretical proposals that we've thought could implement error correction for the first time.
Yeah, that's right.
Okay, got it. And what makes the overall findings from this paper so exciting and significant in your opinion?
So there are two things. I think it was very exciting to be able to use the dynamic circuits capability in the project. Especially this dynamic circuits capabilities has been around for a long time, although to be able to use a system like the quantum systems, the IBM systems that are deployed and available to external users, and these dynamic circuits that people could program it, in a custom way and apply these conditional operations. So that's pretty exciting that anyone could actually run this experiment, right?
Yeah.
Not just someone who is working alongside with the FPGA and the classical electronics experts. So that's one thing. But along the way, when you were looking at the fidelity, we were noticing, wow, this is a very low fidelity, the low infidelity, right? So it's very high fidelity state. And we got very excited, and we did further analysis to compare what we measured with 2-qubit physical state, and then we found that it was break even point. So we had the magic state, the error suppressed magic state that we prepared had better fidelity than if you were to just use 2 physical qubits in a very simple circuit. So that was very important to see. And along that, we actually went into more analysis of the states, and we actually found newer findings that the way that we were looking at, say, the state tomography, reconstructing the state, might not have been the right way. So by during this project, we found that how you correct for the readout error at the end of the measurement is very important. So we actually looked further into that and decided that we were actually just going to publish the results without any error mitigation at the end, so that it is a more true comparison of the states.
Got it. Cool. And what was the key theoretical insight that you guys had that allowed you to achieve this?
If you measure something in quantum mechanics, you project it onto what it says it is. And the way error correction is working, certainly in our experiment, is we just keep measuring and asking the question, like, is this the state that we want? And we keep measuring and measuring and measuring. And every time we become a little bit more certain that we're getting closer and closer to the magic state that we're trying to prepare.
Right.
Every time, and this is how the error correction is working, because if we try and measure and we say, are you the magic state that we want? And it says, no, we're something else, we throw it out.
Okay.
So this is how we get to spot an error.
Gotcha.
So there was a key theoretical insight. So typically when we do error correction, we use what we call stabilizer measurements. And this is nice because we can make these stabilizer measurements in the lab now. And they're very nice theoretical mathematical tools to play with. But what we did in our experiment to make this magic state is we had to go beyond the stabilizer formalism. This is some work I did before I got to IBM with my colleagues in Sydney. We generalized the stabilizer formalism to what we called the XP stabilizer formalism, and we measured things outside the stabilizer formalism to push towards this magic state that we made.
Awesome. What is the key technological or experimental achievement that made all of these findings possible?
Yeah, so there are definitely multiple things that went into achieving these results, but I think the fact that we have a really good device to start with, right? You need to start with something good to even be able to encode into qubits and use it. So we have a very pretty good physical error rates and the coherence time as well. We have pretty long coherence time on these devices, and the fact that we have these classical communications during the circuit using dynamic circuits, that adds a lot of time to the circuit. So it is really important to have long coherence, being able to maintain the state while waiting for this classical communications to happen. So I think those things all together, and then the good thing is that you improve the physical qubit fidelity, so that makes it harder for us to even break the break-even point.
That's
right.
Like, you're like working against your own efforts.
Right, but you do need that really high fidelity to make this work happen as well. So it's very exciting to kind of go, I guess, toe-to-toe, but...
Right. So while you were improving the physical qubits that makes the break-even point further away, you were also working towards that goal at the same time. Right. That's cool. And makes it even more impressive that we were able to achieve that. And I've previously heard a few people refer to this as a gadget. What do you mean by a gadget, and how do we see this being incorporated into other circuits or experiments?
Yeah, that's right. So we have magic state distillation. A bit to my answer before. We need really, really good magic states, and they have to be prepared on very robust codes. So this is going to be a really huge part of a quantum computer that hopefully with more advances and breakthroughs will become easier and easier to do. But I think it's quite exciting that we can actually improve this complicated task of magic state distillation with experiments on the hardware that we're preparing right now. So this little gadget that is making a magic state better than we could, beyond break even, better than we could with the physical qubits on the device. The fact that we can prepare better magic states with this small device can help to encode better magic states into this distillation factory, and could ultimately help to reduce the size of a magic state distillation protocol. So that's exciting. This small little experiment that we ran could really be part of a big magic state distillation machine.
Got it. So in your opinion, what is next for this type of research, both at IBM internally, and also what you hope the broader community can do to build off of it?
Yeah, so what we plan to do next is we're going to look at demonstrating other small elements of quantum error correction and benchmarking these. That'll help guide our path forward. We're also looking at new theoretical ideas to make error correction more efficient. This includes new codes, cheaper ways to do fault-tolerant gates, faster decoding algorithms. And the team as a whole is focused on building hardware for efficient error correction so that we can begin to exercise some of these new ideas. And over the longer term, this will all come together in a new modular architecture for a large-scale quantum computer.
Our experiment is showing that the devices that we're making at IBM are really getting to a place where we could be running big quantum error correction experiments, which will ultimately...
Right, that's huge.
Yeah, I mean, well, not just experiments. I mean, we hope this will lead to a commercial quantum computer in the end. But there's still a big challenge because the cost of large-scale quantum error correction, it takes a lot of qubits. And so this is why we're maybe focusing more on error mitigation right now. And we, obviously, at some stage, we'll believe we're going to need to jump to large-scale error correction, but it'd be nice if that jump weren't so big. So the people at IBM that are building the hardware, they're now trying to make more connected devices, and these types of things are going to help. And at the same time, we're coming up with new theory that can help do better logic gates that can, encode more information with fewer physical qubits. It's really exciting. We've got a lot of ambitious goals, and yeah, it's an exciting time and an exciting place to be working.
I think
but
what's
we're all
really...
going to have to work together.
Yeah, sorry.
It's okay to get to the big goal in the end.
Yeah, I think what's really exciting for me is that, at least when I was in graduate school, it felt a lot of the time like the experimentalists were working in a silo and the theoreticians were working in a silo, and seeing it come together where the experimentalists have built up the hardware to a point where we can now implement theoretical protocols that we didn't know when we would be actually, eventually able to test, and see that come together is, like you said, it's a very exciting time.
It's completely what I could tell you a little story to that if you want.
Yeah, sure.
It's when I was doing my PhD, the theory of quantum error correction would take L by L qubits on a huge grid, and we will want L to go to infinity.
Yeah.
And then an experimentalist comes and say, well, what can you do with 5 qubits? And
right.
Say, well,
I don't want to build that.
Does that number diverge to infinity? He's like, no. Okay. Well, then we were coming up with proposals when Micah was asking me some questions about what do we do with some dynamical circuits? And I said, oh, well, we could do this. It's just 7 qubits. And I thought, great, as a theorist, like 7 qubits, that's not some number that's diverging. And Micah says, yeah, but do you have an experiment with more qubits? I was like, oh, God.
Right.
Yeah, so for this work, right, we were looking at this small code and this distance to, we put the magic state in the 422 code. But in the paper, it goes more into detail on how that could be expanded into a larger code. And for that, you're going to need more qubits and, more places where you're going to use new dynamic circuits capabilities. So, but as along the way, you've probably seen our new roadmap laying out the new directions of how we might want to have more efficient error correcting codes. Right, so we've only been looking at these planar codes, and it's very exciting. So far, we've been looking at memory experiments. We did a distance 2, distance 3 memory experiments on the same heavy hexagon lattice, and then now this magic state preparation. And it's great to make to learn from these planar devices on how you could prepare these states and how you use dynamic circuits in the circuitry. But now we want to also apply the learning that we got from here into the new error correction code that's going to be more efficient.
Got it. Very cool. Thank you so much for your time, Micah. Really appreciate it.
Well, thank you.
Thanks for joining us on our new episode of Quantum Paper Review. I just wanted to take a minute here at the end to thank Micah, Andrew, and Ben again for coming in and having this really educational and worthwhile discussion with us. If you have a paper that you would like us to check out or review, please leave it in the comments below, and definitely check out the Magic State paper linked in the description. Otherwise, we'll see you next time.